Hi everybody. In this video we're going to continue with Chapter 5, Proofs, specifically into Section 5.2, Direct Proofs. So there are four typical methods for proving the implication if P, then Q. In practice, extensive proofs will use quite a few of them. First we have the direct proof, which is where we assume P and logically deduce Q. There's the contrapositive, where we would assume not Q and deduce not P. And this is enough since we know that the contrapositive, if not Q, then not P, is logically equivalent to if P, then Q. This is something we saw in the previous section. Contradiction. Assume that P and not Q are true and deduce a contradiction. Since P and not Q implies a contradiction, this shows that P and not Q must be false. But because P and not Q is equivalent to not P then Q, this is enough to conclude that if P then Q is true. And finally, induction, which has a completely different spirit, and we will consider it in section 5.4. So next, let's take a look at example 5.10. And it says, show that the product of two odd integers is an odd integer. So let m and n be odd integers. We need to prove that m times n is an odd integer. By definition, an odd integer can be written in the form 2k plus 1 for some integer k. Hence, there are integers r and s such that m is equal to 2r plus 1 and n is equal to 2s plus 1. Now notice that here we have to use different variables for the integers in order to prove it for any case. If we use the same variable, we would only be proving it for the same number. Now we consider the product m times n. So this is going to equal 2r plus 1 times 2s plus 1. And then if we expand this, we're going to get 4rs plus 2r plus 2s plus 1. But we can rewrite this as 2 times 2rs plus r plus s plus 1. Since this is an integer and it's in the form of 2k plus 1, we can conclude that m times n is an odd integer. So now let's take a look at example 5.11. And it says, let m and n belong to the integers. Prove that m and n are both odd if and only if the product m times n is odd. So this is an equivalence, right? Remember that the equivalence looks like this. P if and only if Q. So that means that we have to prove this in both directions. We have to prove if P then Q, but also the converse, if Q then P. Now this first part we already proved in example 5.10, where we showed that the product of two odd integers is an odd integer. But now we have to prove that if m times n is odd, then m and n are odd. Okay, let's assume that m is not odd and that m is equal to 2 times k. This would imply that m times n is equal to 2kn, but this is an even number, which cannot be true. So that means that both numbers need to be odd. So this is a kind of proof that can be called proof by exhaustion. We will try an alternative approach in section 5.3. So we continue with example 5.12, and it says, prove the following statement. If m and n belong to the integers, and m is divisible by n, then m is divisible by k times n, where k is any integer. Now remember that we cannot use examples to prove something to be true, but we can use a counterexample to prove a statement false. For example, 18 is divisible by 3 and is also divisible by 6, which is a multiple of 3. However, 18 is not divisible by 15, which is also a multiple of 3. So this counterexample is enough to prove that this statement is false. So let's continue with example 5.13. And it says, prove the following statement. If m and n belong to the integers and m is divisible by n, then m squared is divisible by n squared. Okay, so if m is divisible by n, that means that m is equal to k times n for some integer k. If we square both sides of this equation, notice that we're going to get that m squared is equal to k squared times n squared. Thus, m squared is divisible by n squared. Obviously, right? Because this would imply that m squared divided by n squared is equal to some integer k squared. Okay, so here we are in example 5.14, which will be the last one on this video. And it says, prove the following statement. If n is an integer and n is not a multiple of 5, then n squared has only remainders 1 or 4 upon dividing by 5. So notice that if n is not a multiple of 5, then if we divide a multiple of 5 by n, we would have remainders. We would have remainders 1, 2, 3, or 4. So that means that we have to do a direct proof by cases. Now, first case is if n has remainder 1. In this case, we can write n in the form 5k plus 1. So if we go n squared, notice that n squared is going to equal 5k plus 1 squared, and this is going to give us 25k squared plus 10k plus 1, but this is going to equal 5 times 5k squared plus 2k plus 1. So notice that we get a remainder 1. Second case, n has remainder 2. So here we can write n in the form 5k plus 2. We proceed in the same way. We go n squared is equal to 5k plus 2 squared. And here in the end, we're going to get 5 times 5k squared plus 4k plus 4. So this would have a remainder of 4. Third case, n has remainder 3. So n we can write as 5k plus 3, and then here we're going to get that n squared is going to be 5 times 5k squared plus 6k plus 5 plus 4. Therefore, remainder 4. And the last case would be n has remainder 4. So n we write in the form 5k plus 4. And then here, if you do the math, you're going to get that n squared is going to equal 5 times 5k squared plus 8k plus 3 and plus 1. So that means that we would get a remainder 1. Therefore, we can say that n squared would only have remainders 1 or 4 upon dividing by 5.